Today's starter is all about the Curiosity rover that's landed on Mars. Now the Curiosity rover, which landed in 2012, landed with a mass of 899 kilograms. Now how much would that weigh on Earth in newtons? But how much does it weigh on Mars in newtons? And I have to give you some information about the mass of Mars and the radius of Mars. They're right there. And then, now the Curiosity rover, it bounces signals off a satellite that's around Martian orbit, the Mars Reconnaissance Orbiter. And it has an altitude of 300 kilometers above the surface of Mars. So what is the orbital speed of that? So let's do given, find, and solve. So given, we've got Mars. Let's do. So we got Mars, and we're given its radius. And then we're given its mass, and I'm just going to refer to that. I don't want to rewrite those numbers. And then we have a satellite that's in orbit, and its height above the surface, h, is 300 kilometers. And then the Mars Reconnaissance Orbit, I'll just draw it like a little thing right there. It has a mass of 899 kilograms. And so what are we trying to find? Well, what is the force of gravity on the Curiosity rover on Earth? And then B, what is the force of gravity on Mars? And then part C, what is the orbital velocity of the spacecraft in orbit that it's using to communicate with Earth? All right, so now let's solve. Oops, let me zoom out. Screen. Well, let's do A. The force of gravity is equal to the object's mass times the gravitational field on that planet. Well, the mass is 899 kilograms, and it's on Earth. It's 9.8 newtons of force per kilogram of mass. And when you do the arithmetic, you get 8,810 newtons. Now, by the way, there's 4.45 newtons in 1 pound. So if I divide that by 4.45, and you didn't have to do that, that's almost a ton. It's 1,900, and now I'm just going to put 1,980 pounds, since you guys are more familiar with thinking about things in terms of pounds. So it's like a small car. They put a small car on Mars. Okay, no gas needed. It's nuclear powered. All right. Now on Mars, the force of gravity equals mg again, right? But we don't know what g is. Well, but we do know what the mass of Mars is. We know the spacecraft's mass, and we know what the radius of mass. So I can figure out what g is. G m over r squared, right? That's the force of gravity between two massive objects. So that's 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Yes, I'm going to write all the units down. So should you. All right. And then the mass of Mars is 6.39 times 10 to the 23 kilograms. Now, Earth is about 6 times 10 to the 24 kilograms. So Mars is about 1/10 the mass of the Earth. So it's not very big compared to the Earth. And then the mass of the spacecraft. And then it's on the surface, so we just use the radius. And we square it. So that's a lot of arithmetic. Let's see what we get when I do all that. So let's clear. 6.67 times 10 to the negative 11 times 6.39 times 10 to the 23 equals times 899 equals, and then we're going to divide that by 3.4 times 10 to the 6, and then we have to square it, and I get 3,315, if you round it off, newtons. Now, notice that this spacecraft weighs a lot less on Mars than it does on Earth, right? It's a smaller planet, has a lot less mass and a smaller radius, so that kind of makes up for a little bit of it, but not all of it. So, yeah, that's about a third, isn't it? A little over a third. Now, part C. Oh, now what would that be in pounds? Divide it by 4.45, and that's about 745 pounds. It weighs about 745 pounds on Mars. So if you're an engineer and you're designing this this probe or this rover, you need to design it to take that weight. Well, it also has to survive launch and re-entry and all that, so there's some really big forces there. So there's a lot of things to consider when you're designing these spacecraft. But anyway, a spacecraft is in orbit around Mars with an altitude of 300 kilometers. So we know that the orbital velocity equation is gm over r. Okay? Right? Yeah, that should be on your equation list. I see some of you smiling. Okay, so this is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And then we're going to multiply that times the mass of Mars, which is given to be 6.39 times 10 to the 23 kilograms. And then we have to divide it by r. Now here's where people mess this up. People are getting sloppy. Don't get sloppy now. This is the radius of the orbit. And we know that the radius of the orbit is the radius of the planet plus my height above the planet. So this is going to be 3.4 times 10 to the 6 meters plus, now, folks, listen to me. This is why I always write units down, and I see people making this mistake all the time. Then they add 300 to this. No, you're not adding 300 to it. What are you adding? 300,000 to it. Because I gave the height in kilometers. It's got to be in meters. Kilo means 1,000, so 300,000 meters. Don't forget to do that on the test. Okay, so 3.4 times 10 to the 6, thank you, plus 300,000. I should be able to do this in my head. It's 3.7 times 10 to the 6 meters. Now, you could have done this in here because look at this number here. This is like 0.3 times 10 to the 6, isn't it? If I move this over 1, 2, 3, 4, 5, 6 places, that's 10 to the 6, 0.3 times 10. And why did I want this to be 10 to the 6? Well, this is 10 to the 6. So now I can just go 3.4 plus 0.3. Well, that's 3.7 times 10 to the 6. Now I can plug that in over here. Oh, why did I write that up there? Now so this is 3.7 times 10 to the 6 meters in here. So let's do the arithmetic one more time. 6.67 times 10 to the negative 11 times 6.39 times 10 to the 23 divided by 3.7 times 10 to the 6 equals, and I get, whoa, that's really fast, 1.15 times 10 to the 7 meter. That's like 5% of the speed of light. It's probably the wrong answer, because I forgot to take the square root, which about a fourth of you will do on the test. You will do everything right, and then you'll forget to take the square root. How sad. All right, so raise that to the power of 0.5, and I get the correct answer, which is, I hope, 3,394 meters per second. Is that what you got? Anybody get that? Now, that's pretty slow compared to what you'd have to be in orbit around the Earth. I think Earth is like 7,000 meters per second. So, anyway, there you go. Any questions on this starter problem? Okay, that is